The second part of the course for the manufacturing of die casting dies according to Nadca 207 is intended for material selection and testing. The material selection, the way it is ordered, and the control of delivery have a fundamental influence on the result. Therefore, we will cover this chapter in great detail. Correct material ordering is a critical step in the die casting dies manufacturing process with a significant impact on the resulting tool life. And faults in this process can never be corrected. To understand the difference between different grades of steel, let's give an illustrative example of what we will talk about. Let's imagine that we have two completely identical Skoda Fabia cars. From the outside, there is no difference between them. However, if we open the hood, we will find that each car has a completely different engine. One with an output of 51 kilowatts, the other with an output of 135 kilowatts. In terms of driving characteristics, these are two completely different cars, and the price will also differ accordingly. The same criteria will apply to the material. At first glance, both materials are the same. However, if we look inside at their structure, we will see a completely fundamental difference. One has a fine-grained structure without obvious defects. The other has a coarse-grained structure, high line density, and other defects. The key question is how to recognize this in advance. For a car, we order the first or second version according to the catalog. But how to recognize this when choosing steel? As already mentioned in the introduction, there is a demonstrable correlation between a material's resistance to thermal fatigue, cracking, and impact strength. The higher the impact strength, the higher the material's resistance to thermal fatigue, and vice versa. If we compare the results according to the graph, the difference between good and bad toughness can lead to a 2- to 3-fold deterioration in thermal fatigue resistance. However, since this is a property that must be ensured by the steel manufacturer, our duty is only to purchase the steel correctly, and after purchase, to check whether the performance corresponds to the specification. The first question is, why impact strength, when there are a number of other analytical tools to detect structural defects in a material? However, the impact test is unique in that it provides cross-sectional properties of the material, which, though average the effect of possible material defects, are sufficiently sensitive to these structural defects. At the same time, from the point of view of costs, it is a test where we get the result at an acceptable price and in a reasonable time. This is very significant because with the frequency of testing, Nadca is approaching the standards for the aerospace industry, where every heat number, every batch, and in some cases even every piece, must be tested and validated for certain mechanical properties. For this reason, air travel has become the safest way to travel, and this testing will have the same impact on die casting dies. The second question is what affects the toughness of the material and how to prepare such a material. This is especially important for steel manufacturers, as they are responsible for the key properties of the material. The third question is what mistakes to avoid when purchasing material for shaped inserts in order to exclude material defects that reduce the toughness of steel. This is especially important for tool manufacturers and the tool's users. We will tell all this later. The first basic condition for high toughness is the minimum content of primary carbides in the structure. We will talk about what primary carbides are later. For now, it is only important that their presence in the steel structure demonstrably significantly reduces the impact toughness, and thus the resistance to thermal fatigue. It can be seen from the figure that it can lead to a 5 times deterioration. The second basic condition for high toughness is a fine-grained structure. Again, there is a correlation between grain size and material toughness. The finer the structure, the better the result. The minimum requirement is a grain size of 7. From the above graph, it can be concluded that, with regard to the austenitic grain, there can be a 3 times deterioration of the mechanical properties measured through impact toughness. The third criterion for maximizing the toughness values is the phase transformation of the structure during hardening. If we compare the values for martensite, bainite, or perlite, we see that the maximum values of toughness can only be reached when quenching to a martensitic structure. The proportion of bainite or the proportion of perlite in the structure fundamentally reduces the toughness. The resulting impact strength will therefore be highest for a fully martensitic structure, lower for a structure with bainite, and lowest if perlite is also present in the structure. If we compare the values of the impact test for martensite and for perlite, deterioration can occur up to 5 times. The fourth criterion will be the cooling rate during quenching. This must be sufficient to exclude precipitation of carbides. Since there is a CCT diagram for each type of steel, it is easy to read from it what cooling rate is needed to eliminate these precipitation processes. The orange area on the diagram represents precisely the area of carbide precipitation. At the bottom left of the martensite start red line is the martensite area, and on the right is the bainite area. In the upper right, there is an area with perlite excretion. Therefore, in order to pass the area of carbide formation, and at the same time have a 100% martensitic structure, we must cool down at a rate of at least 28 degrees Celsius per minute for materials of grade H11 or H13. If we cool at this rate or faster, our structure will be okay. If we are to the right of the green cooling curve, the structure will be defective. The last criterion is the exclusion of the area of formation of secondary carbides during tempering. These are also particles, worsening the toughness of the material and reducing resistance to thermal fatigue. Since these carbides precipitate in the range of tempering temperatures from 500 to 550 Celsius, this area must be excluded from processing. The minimum tempering temperature for steels such as H11 or H13 is 565 Celsius, but there are also steels where this temperature must be even higher. For example, for QRO90 steel from Uddeholm, it is at least 600 Celsius. So now we already know with which basic parameters we can influence the toughness of the material, which is necessary to limit the occurrence of cracks from thermal fatigue. But these are only basic criteria. There are 10 of these criteria in total, and they are listed in the Nadca specification under the letters A to J. However, before we deal with their detailed content, it is necessary to look at the steel production process. This is key to obtaining the appropriate material quality. The first step is to produce pig iron from iron ore in a blast furnace. This pig iron contains up to 5% carbon and a number of other impurities related to the raw materials used. Pig iron in a liquid state is then transported to electrically heated furnaces. Here it is mixed with steel scrap and other slag-forming additives, and at a temperature of 1,350 to 1,400 Celsius, the carbon, phosphorus, or sulfur content is reduced to the required level by the deoxidation process. Basic alloying of the steel is also carried out in this production step. In the next phase, the melt is processed in so-called secondary metallurgy furnaces, where the carbon content is reduced to the required limit, and the chemical composition of the steel is adjusted by adding some elements or reducing others. The result of this secondary melting process is steel with the required chemical composition, but it may contain a large amount of unwanted impurities in the form of non-metallic inclusions or globular oxides. Although the limits of these impurities are defined by standards, they are so wide that this steel can have very diverse properties. from the good to the bad. An ingot is then cast from the steel prepared in this way. Its properties correspond to the purity of the material from the secondary melting process. This can be clearly seen in the picture from the Böhler Company, where the isodisc quality shows how wide the tolerance field of material purity is for steel prepared in this way. Of course, the resulting impact strength also corresponds to this. It is possible to purchase material that will have properties corresponding to remelted steel, but also material that will be significantly worse. There is therefore a high risk that using steel produced in this way in a die casting dies will not achieve the necessary tool life. In order to eliminate these risks, another operation is included, the so-called steel remelting. The ESR, electroslag remelting process, or VAR, vacuum arc remelting process methods are most often used. In the VAR method, the entire process is carried out under a high vacuum at a pressure of up to 10 Pascal. The Böhler Company uses the abbreviation VMR for this process. It means vacuum melting and refining. The remelting process is based on the reaction of the melt with the slag, which is composed of highly reactive materials such as calcium fluoride, calcium hydroxide, aluminum oxide, and others, and which have the task of reducing the concentration of undesirable elements or inclusions in the steel. This remelting process can be applied once, but also twice or 3 times, depending on what requirements are placed on the final material. The result of this remelting process is a higher purity of the steel, a lower amount of micro-segregation, unwanted elements such as phosphorus and sulfur, and a better microstructure of the ingot. So we get a steel whose impact strength is close to the maximum yield of the material, and above all, it has a narrow tolerance band. This is exactly what we need for die casting dies. High and stable impact strength values. Despite all efforts to improve the steelmaking process, it is still a heterogeneous process with different properties in different parts of the ingot. This also applies to the microstructure and grain size. In order to refine and flatten the large grains from the ingot solidification process, the entire ingot must be reforged. A 5:1 ramming ratio and 3-dimensional forging are recommended. The goal for the material according to the Nadca 207 specification is to refine the grain to at least size 7 and above. For the most demanding applications, a higher grain size value, for example 10, can be ordered. The grain size is defined as the number of grains per unit area. This means that the higher the number, the finer the grain structure. This results in a greater resistance of the material to crack propagation. Because the base block from which the steel supplier supplies the individual blanks for the die casting, die inserts is heterogeneous. The grain fineness in the surface areas is better than inside the block. Since the mother block is a steel block weighing, for example, 7 tons, then of course the material inside the block has different properties than the material from its peripheral parts. This must be kept in mind when ordering material. If we want to be sure of the quality of the material, we must also specify the grain size to the steel supplier. The steel supplier must then find a place on the block that has these properties and cut the material for the insert from it. Failure to comply with the grain size when receiving the material in the tool shop is a reason to reject the material at the input and replace it with new material. All costs associated with this should be borne by the steel supplier. However, it is also necessary to realize that the grain size can change as a result of heat treatment or tool use. Therefore, this parameter must be evaluated at the input, not after the insert is damaged in the foundry or after heat treatment. One of the problems that material from primary manufacturing process has to deal with is the size and distribution of the primary carbides. These are carbides of various alloying elements, such as chromium, molybdenum, vanadium, which are not dissolved in the matrix, and whose size is greater than 5 microns. These primary carbides are part of the purchased condition and significantly affect the impact strength of the material. The less dissolved and the larger they are, the lower the impact strength. This connection is clearly proven, and the steel supplier must be able to treat it. Therefore, homogenization annealing is applied to the already forged material precisely for the purpose of dissolving and refining the primary carbides. This annealing takes place at high temperatures above 1,100 Celsius, and for a period of 24 hours or more. After applying all previous operations and before delivering the material to the customer, the final soft annealing of the material must still be performed. This is an isothermal spheroidizing annealing process important for the machinability of the steel, reducing the final hardness of the material and improving plasticity and toughness. Soft annealing is carried out at temperatures of 840 to 870 Celsius. Staying at the annealing temperature is recommended for 2 to 4 hours. Cooling from the annealing temperature should be controlled at a rate of less than 33 Celsius per minute to a temperature of 590 Celsius. Cooling in air follows. The resulting structure should not have a hardness higher than 235 Brinell's units, according to Nadca 207. Acceptable annealing structure maps are part of the Nadca recommendations. Based on them, a partial initial evaluation of the material can be carried out, and those that do not conform to these maps can be excluded. It follows from the previous operations of primary steel production that the road to quality steel is not easy. That is also why Nadca 207 says which steels can enter the system, from which manufacturers, and the others only on the condition that they meet certain parameters, the control of which is difficult. Nadca 207, version 2025, now registers approximately 42 steels from various manufacturers according to the table, and various steels of type H13 in premium or superior quality. Approved suppliers are Swiss Steel International, Udehome, Böhler, Kind & Company, Obert Duval, SYJ, Metal Raveny, Dido, Elwood, Sanyo, or Nippon. Only these steels may enter the dies manufacturing system according to this specification, and in accordance with CQI 27. As you can see from this list, new steels are constantly being added as steelmakers improve. It is therefore necessary to keep track of what Nadca 207 enables. So finally, we come to the material specification for die casting dies. There are a total of 10 control operations that must be fulfilled. Condition A. The steel must be Nadca grade, specifically listed in the Nadca regulation, groups A to H. Condition B. The annealed structure for both premium and superior quality must have a maximum of 235 Brinell. Condition C. The chemical composition of the steel should correspond to the chemical composition of steels according to the Nadca 207 table, especially the content of undesirable elements, phosphorus and sulfur, should be observed. All other alloys should be within the permitted tolerance band. The next condition in order is Condition D. The material must be produced in sufficient purity with the content of non-metallic inclusions according to the table. The purity of the material differs for steels of series A and F, and for series B, E, G, and H according to the Nadca specification. In all cases, the purity of the steel is evaluated according to the American Standard ASTME 45, Method A. Condition E. All blanks must undergo an ultrasonic test, proving that the material is free of internal defects, non-metallic inclusions from slag, large oxides, cracks, etc. This test is conducted according to the American standard A681 and should demonstrate that the material does not show any significant internal defects. Condition F, austenitic grain size. This data is evaluated according to the American standard ASTME 112 on a metallographic cut and tells how many grains are present on a defined surface of the sample at a magnification of 100. The samples for evaluation are prepared by controlled oxidation at austenitizing temperature followed by rapid cooling. The minimum for die-cast inserts is size 7, but there are related corporate standards that allow a minimum grain size of 9 and above. Condition G. Part of the material specification is the evaluation of the annealed structure when entering the tool shop. Nadca 207 contains maps of annealed structures which are acceptable and which are not, and on the basis of this simple test, the input material can be excluded according to quality. The test can be performed on a metallographic sample, but it can also be performed directly on the block, where a small surface is ground, polished, and etched, which is then analyzed, for example, using a special portable microscope at the required magnification of 500. Condition H. Any steel prepared by forging or rolling exhibits some degree of microsegregations banding. This is manifested by the arrangement of one or several structural components in rows, usually in the direction of longitudinal hot forming, for example, rows of perlite, carbides, or non-metallic inclusions. Linearity is evaluated on the annealed structure at 50 magnification, and the result is compared to Nadca 207 maps with acceptable and unacceptable structures. Nadca 207 differentiates materials into two basic groups, Class 1 and Class 2. Both groups have the same testing conditions, except for point I. Impact tests are mandatory for the Class 1 group, and these tests are not required for the Class 2 group. Therefore, if we want the material to be classified according to the Class 1 group, we must perform impact tests according to Condition I. In Condition I is stated that the input material, Class 1, needs to be tested for impact strength to get the overview about steel capability. This test is performed on all delivered blanks with a thickness greater than 2.5 inches, approximately 63 millimeters. The test must be performed on each delivery from the mother block separately. Sample material is taken in the least favorable direction, perpendicular to the direction of the fibers from the forging or rolling of the steel. The coupon for these samples must be of such a size that 5 V-notch impact test samples can be produced from it. Specimens must conform to ASTM A370-05. The semi-finished product in the annealed conditions is quenched ideally in oil from the prescribed austenitizing temperature and is tempered at least twice to 590 Celsius with a final hardness of 44 to 46 Rockwell. Final samples with a V-notch are then made from the coupon, and these samples are tested on a device called a Charpy hammer. The device for the Charpy test must be calibrated according to the American standard ASTME 23 or according to ISO 148 in the latest version. Impact strength values from individual samples are recorded and further processed into a test report in accordance with Nadca 207. The lowest and highest value are not taken into account. The average value is calculated from the remaining 3 measurements. This must correspond to the table values for the given material according to Nadca 207. The last condition J is more or less already formal. For each material, the method of remelting should be indicated, for example ESR, PESR, VAR, VMR, etc. So how do you apply Nadca 207 steel purchase conditions in practice? It's much easier than it seems. If we translate all the rules A to J into human language, it is a guide to how to properly place an order for material. This is the most important conclusion. So what should such an order look like? See an example of an order with all the details. For practical purposes, however, it is necessary to state that the most important information on the order is a reference to the Nadca 207 specification. This reference makes the parameters according to Nadca 207 binding on the steel supplier as part of the material purchase contract. The order will only contain details that differ from the Nadca specification or cannot be defined. These include, in particular, the steel grade, block size, price, block weight, banding orientation, grain size, and instructions for cutting additional material for testing. The order will state that payment for the material will only be made after the steel test has been carried out and passed. It is also necessary to indicate whether it is Class 1 or Class 2 processing. In the case of Class 1 processing, impact tests are mandatory, and in that case the steel supplier must prepare a blank for the coupons, even if we neglect to mention it in the order. If we want a grain size greater than 7, then we must also state this requirement in the order. On the basis of such an order, the steel supplier has an exact specification of what to find in stock, how to cut it from the mother block, or how to cut the coupon for impact tests. It also has a precise specification of block properties, including a narrowed band for the austenitic grain size. Other material properties are provided by reference to Nadca 207. If we want to order material for the Class 2 group, a simplified order with only reference to Nadca 207 and Class 2 is sufficient. Everything else follows the specifications. In this case, too, the steel supplier is obliged to deliver material according to points A to J, with the exception of point I. Since the impact strength test is not mandatory in Class 2, we do not need a steel blank for coupons. Unfortunately, we have to pay for the order according to the steel supplier's due date. Although the input tests according to Nadca 207 are mandatory, the entire specification is a recommendation. However, it is in the interest of the tool manufacturer to verify that what was ordered is also delivered. Nadca 207 says exactly what the tool shop should do and how to ensure these input tests, so that they are demonstrable and objective. At the same time, the results of these input tests will also be the basis for making a claim and possible compensation for damage if the required tool life is not achieved. This must always be remembered. If this were not the case, it is quite certain that we lose this information for a possible material claim, and it is also obvious that without these tests, it will be very difficult to prove fault on the part of the steel supplier or foundry. In the event of a possible lawsuit, there will be a so-called evidentiary shortage. The initial state of the steel is not known. The price for the input impact test represents the price for the added material and for the tests themselves. It is also necessary to take into account that this initial quality testing will take about 5 days, because we have to ensure the quenching of the coupon in oil and its testing in a certified laboratory. The price for the added material for the coupon will be approximately €50, and we will pay up to €200 for the tests. If we really consider the initial impact tests to be economically and time inconsistent, we can only purchase a cut of material and archive the coupon for the tests. The initial test can be performed at any time subsequently, only when the mold user complains about the service life. It can therefore also be proven subsequently whether the input material was OK or NOK. According to the Civil Code, hidden defects can be claimed within 2 years of receipt of the goods. This is the time for us to have these coupons in the archive. Tool shops are usually concerned about the time delay in the production of the insert with regard to the application of impact tests according to Nadca 207, Class 1. In order to be able to plan this time schedule, we need to know the estimate of the necessary times. As soon as the tool shop receives the block of steel according to the order, it must ensure that the blank for the samples is cut. We need about 1 day for this operation. It must be said that the tool shop does not produce samples, but only and exclusively a test coupon. The preparation of V-notched samples requires special procedures, and these can only be provided by a certified laboratory. Subsequently, the tool shop sends the coupon to the heat treater for hardening in oil according to the specification. We need 2 days for this quenching and 2 temperings operations. After the heat treatment, the heat treater usually sends the coupon for the initial impact tests to the testing supplier, who tests them within 48 hours. The test report is sent electronically without a time delay. So it can be said that within 2 days after the quenching of the samples, you can have a confirmation that the material complies or does not comply with the specification. A total of 5 days are therefore needed for the input verification of the material. That's not enough. But if we choose this path, we are sure that the material is okay. But if it's not okay, then we don't have to pay for it, and the steel supplier has to supply another material with the necessary properties, as well as pay for any damages. If we choose the archiving route, then we have to pay for the material by the deadline according to the supplier's conditions without knowing whether it was okay or not, and we risk bearing the costs associated with a claim if the required service life is not reached. The picture shows an example of a certificate from Element Laboratories. In this case, it was an evaluation of the input quality of the material 1.2344, or H13 Group B steels, according to Nadca 207, with the required values for the annealed material on average 13.6 joules, the minimum value 10.8 joules. The tested sample met the expected values and the block material could be released for production. Not all samples show acceptable results. The statistics of the long-term monitoring of input impact tests show that 13% of the supplied material does not meet the conditions of Nadca. This is a high percentage, considering that several thousand tons of this type of steel are sold annually. Since each block is tested even after heat treatment, it is proven that if the material does not pass the input tests, it will not pass the tests after the heat treatment either. This only confirms the fact that no heat treatment can improve the material. We can only maintain or worsen its properties. The purchased condition is therefore absolutely essential for the future life of the die. But there is one more risk. If the tool shop does not perform the input test, and the test after the heat treatment of the real insert is unsatisfactory, the blame falls on the heat treater shop, even if the origin of the problem is in the condition of the steel purchased. The heat treatment provider thus finds itself in a disadvantageous position, where it will have to prove that it is not to blame for the not okay result. The step-by-step procedure is shown in this table. It shows how the tool manufacturer will respond to the result of the input material test and the result of the test after hardening of real insert. Now let's recap what was said in the previous part of the training. The material must be Nadca grade, that is, it must be selected from a list of approved steels from approved suppliers. The input annealed structure must not have a hardness higher than 235 Brinell units. The chemical composition must correspond to the table values of Nadca. The material must be produced in sufficient purity, with the content of non-metallic inclusions according to the table. All blanks from the parent block should be subjected to an ultrasonic test to detect cracks, voids, and inclusions. The grain size must be at least 7, graded according to ASTM E112. The microstructure of the annealed condition must be conformed to the Nadca charts for acceptable annealed structures. The microsegregation of the annealed structure must not deviate from the acceptable structures according to the Nadca maps for the banding segregation of steel. In the case of performing impact tests, the following values should be given. Impact capability test result of the supplied material. 5 individual impact test data, their average value for 3 of them selected for average value calculation. Heat treatment data and resulting hardness should be provided. For each material, information on the method of remelting ESR, VAR, or another alternative method should be given. Each delivery of steel, according to Nadca, should be accompanied by a certificate that will contain all the previous information according to conditions A to H and information about condition J. This information should be supplemented with condition I in the case of processing in Class 1, meaning with impact tests of the input quality and after hardening. Failure to apply the rules of the Nadca specification in practice brings risks. The basis of success is a correctly conceived order. High risk occurs if the incoming material inspection is not carried out at all, or if the material is used in an unremelted condition, and at the same time, impact tests according to Processing Class 1 are not applied. Medium risk occurs when remelted material is used, but at the same time, impact tests according to Processing Class 1 are not applied. Low risk occurs when remelted material is used and the entire Processing Class 1 process, including impact tests, is applied at the same time. The course material selection and testing is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.